Okay, so I guess we'll get started. Today we're happy to have Harry Desmond from Oxford. Harry is a postdoc at Oxford, currently working on different ways to study for the boards and galaxies. Harry has also worked quite a bit on galaxy scaling relations and the relationship between galaxies and the dark matter nebulae they form within. And has worked quite a bit on various ways to push those relationships to the brink and see where current pictures of the galaxy halo formation or galaxy halo connection might fail. So if you're interested in talking with him about any of these topics, he'll be here until Wednesday. And he's upstairs in his office. Feel free to stop by. We'll also be taking him for dinner tonight around 6 p.m. I think, so let me know if you'd like to join. And other than that, take it away.
Okay, thank you. So I'm going to be talking about some work that I've been doing in the past year and a half or so since my PhD with Pedro Ferreira mostly at Oxford on searching for fifth forces in galaxies. So I'll start with some overview of why we should be motivated to look for new physics, why specifically the galaxy scale might be an interesting one to do that in. I'll describe the phenomenology of this new physics in terms of fifth forces. Then I'll tell you a bit about the analyses that I've done to actually concretely try to test them. And what that amounts to is mapping the local universe in gravitational variables to try to determine which objects should exhibit this fifth force and which shouldn't. And then doing some Bayesian inference on the parameters of this potential new force. Okay, so to start with some motivation, obviously I don't need to tell you that lambda CDM works incredibly well on a huge range of timescales and spatial scales. So it works well right from BBN through recombination, CMB, gives you growth of structure, expansion history of the universe, right down to halo abundances and clustering at redshift 0. So you might wonder from that, maybe we're done. I mean, why are we trying to invent and test new physics when we have a picture that seems to work so nicely already? So I'll give you two motivations for why we should still do this, one of which is more sort of traditional, and one of which is a sort of newer way of thinking that's been gaining ground recently. So the first one is that, of course, we have to put a number of funny things into the standard model to get it to work. Not least of which is dark energy, something we don't really understand at all. And we're sort of stuck between a rock and a hard place with dark energy. On the one hand, we can call it a cosmological constant, put it on the left side of Einstein's equation, in which case it's 55 plus orders of magnitude too small, given what we think we understand about quantum field theory. Or on the other hand, we can put it on the right-hand side and call it a new type of matter, call it dark energy, in which case we, again, don't know where it comes from, and it has peculiar properties, like having negative pressure. So one of the hopes in modified gravity for a long time has been to come up with a dynamical explanation for the phenomenology of dark energy, namely the accelerated expansion of the universe. So it normally goes by the name of self-acceleration. The idea would be that you would have just conventional matter fields, but by modifying the Einstein-Hilbert action, that could naturally lead to an acceleration of expansion. And the second motivation is just that there could well be new dynamical degrees of freedom in the basic Lagrangians of particle physics and cosmology. New light scalar fields, for example, they arise naturally in a number of ways. And if we can develop new ways to test for them, then we should. Okay, so now let me try and motivate why the galaxy scale is an interesting one for doing this. So this is a plot from Tessa Baker at Oxford from a few years ago, which is trying to parameterize possible tests of Einsteinian gravity. So what we have on the axes are two fundamental measures of gravitational field strength, Newtonian potential and space-time curvature. The points and objects on the left here are various systems, where these systems lie in this parameter space. And on the right are the corresponding experimental or observational tests that we have of these systems. So for example, we have parameterized post-Newtonian tests in the solar system. We have tests of compact objects, gravitational waves, pulsar timing. That happens at high Newtonian potentials. Black holes, for example, have potentials near 1. And then we also have cosmological tests down here at very low curvature scales. So BAO, power spectra, Planck, and that kind of thing. And you'll notice that there's this sort of gap in the middle. And in the paper here, they called that a desert, where we really have no tests of gravity at all. So very roughly, we have three regimes on this plot, right? We have small-scale tests, which are within the solar system or within or around compact objects. And we have cosmological ones. And in the center is the galaxy scale regime. And you'll see that there's nothing really here. So part of the point of this is just to show that simply by having tested general relativity in this regime and in this regime, that doesn't mean we've tested it full stop. It's quite easy for there to be modifications that would kick in at particular potential or curvature scales that we simply wouldn't see by having tested it here or here. And in fact, you might think that it's reasonable to expect modifications to GR to kick in precisely here. So we think that we understand small-scale objects' structure very well. And in cosmology, we have to do dubious things like introduce dark energy. So if there was some modification to physics that was going on, then it's reasonable to think it would happen at these intermediate curvatures. So that's one reason why galaxies are interesting. Another one is that there are, in fact, a number of quite well-motivated general modified gravity theories that do precisely this, that precisely manifest their effects in galaxies while explicitly reproducing GR at these high curvature scales in the small scale regime, and also having very small effects in cosmology. And those are theories with screening mechanisms, which I'll come to in a second. And finally, you might think from this plot here that we don't really have much data on galaxies. There's just nothing here. But of course, we have a huge amount of data on galaxies, and we're getting more and more all the time. We just haven't used it to test gravity yet. So that's really the focus of the program that I'm trying to develop. OK, so now let's talk about some of the phenomenology of new physics that could come about at the galaxy scale. And here I'll try to be as generic as possible. So basically, the most general thing that happens whenever you try to fiddle with the Lagrangians of Einstein, of GR or particle physics, is you introduce new dynamical degrees of freedom. So these come about from effective field theories breaking down, symmetries being broken, higher derivative terms in the Lagrangian, extra dimensions, promoting constants to dynamical fields. Essentially, anything introduces new scalar vector or tensor fields into your Lagrangian. And what those do is they naturally couple to matter and introduce new interactions between masses. And that generically goes by the name of a fifth force. It's a new force of nature besides the four that we already understand. So if I focus on the case of a scalar field for simplicity, then the form of the new interaction looks like this. So instead of just having a Newtonian potential describing the interaction between two objects, you also have this extra term that's characterized by properties of the scalar field. And in particular, two properties: the strength of the interaction relative to gravity, which I'll call delta G. That's just set by the coupling of the scalar field to matter. And the range of the force, which is given by the mass of the scalar field. So if you have a high mass field, then that induces a short range force, and vice versa. OK, so we can go out and test for this quite easily. Effectively, what this is a breakdown of the inverse square law. So instead of just having normal Newtonian gravity, you have this extra Yukawa force that cuts off at some particular scale given by the mass of the new field. So there are a number of tests that we've been doing for some decades to try to search for these. On small scales, the thing to do is these kind of Iot-Vosch torsion balance experiments, where you look for forces between two objects nearby and how that force varies with composition of the object or separation of multiple objects. And on larger scales in the solar system, we can use lunar laser ranging, planetary orbits, and there's also a very nice test based on radio link to the Cassini spacecraft that went to Saturn, which tests for the parameter in the parameterized post-Newtonian framework that describes how light is relatively bent and delayed by going past a source, in this case going past the sun. So the upshot from all these things is very strong constraints on what the strength of this fifth force can be. And so strong, in fact, that if the force is universally coupled to all matter, then it has to be essentially irrelevant in astrophysics or cosmology. But that's not the end of the story, because the force doesn't have to be universally coupled. And in fact, in the last couple of decades, we've come to understand that there are a number of quite natural ways of having the coupling between objects via this new force depend on environment. And that goes by the name of screening. So the basic point of screening in a nutshell, is to do this. So in high density regions, for example, all of these tests down here, the lab is, cosmologically speaking, a high density region. Similarly for the solar system, anything within the Milky Way. In high density regions, the fifth force decouples, and so you just reproduce GR. And in low density regions, the fifth force can reappear, and so it can do interesting things in, for example, dwarf galaxies that are much, much less dense, or in cosmology as a whole.
Density of what?
Pardon?
You say high density of what?
Yes, good. That's exactly what I'm coming to. Exactly, high density of what? So there are a few different flavors of screening mechanism, and they vary precisely in how they interpret high density, as in what exactly it is that characterizes whether a system is high density or not. So I'll describe what they are, and then in the next slide I'll show you what that means for whether an object is actually screened, whether it's in a high density region or not. So the first one to be found actually is called Chameleon Screening. So the way that works is that the effective mass of the scalar field becomes very large in high density regions. So the range becomes very small when it effectively decouples from matter. F of R, for example, screens by chameleon. Kinetic screening works by having the kinetic term in the Lagrangian become large in high density regions, which suppresses the coupling again. And then there's Symmetron and Weinstein, which work by setting the strength of the fifth force essentially to zero. So some of these figures show these things, and I apologize that they're a bit small and you probably can't see them. So this here is intended to demonstrate chameleon screening. So what's going on is we have some massive object deep inside the object where it's very dense. The effective potential, which has a term that depends on density, acquires this relatively highly curved minimum, which corresponds to a large mass. So this part of the object essentially has no scalar charge. It doesn't couple to any other object by the fifth force. Whereas in the lower density outer parts, you have this more broad minimum of the effective potential, which corresponds to a smaller mass, and hence a longer range of interaction that allows it to couple to other bodies by the fifth force.
What are the axes
Of these plots? So the y-axis is effective potential, and the x-axis is scalar field strength. It's the same axes as here, actually. Yeah. So this is symmetron. What happens here is that the scalar field has a Z2 symmetry, so it's symmetric under phi goes to minus phi. But in low density regions, that symmetry is spontaneously broken. So you have two possible solutions with finite non-zero values of phi. And the coupling of the field to matter is proportional to the strength of the scalar field. So in low density regions where phi is non-zero, you have a non-zero coupling of the field, you have a fifth force. Whereas in these high density regions, the field just sits around zero, so it doesn't couple to anything. And in Weinstein, you just have a specific radius around a given body called the Weinstein radius, beyond which the fifth force kicks in, and within which it goes to zero. Okay, so now coming back to the question of how do we interpret high density. So I've shown again these three mechanisms here. This is the term that dominates at high density, and which effectively decouples the fifth force. And this column here is the observational proxy for degree of screening, as in this is the variable that determines whether an object would be said to be in a high density region or a low density region. And I give you a very hand-wavy explanation for why these should be the observational proxies. But for more information, you should have a look at this excellent set of lecture notes by Justin Curry at the Les Houches Summer School in 2013, which lays all this out. So the very hand-wavy explanation is that so the mass of the scalar field is the coefficient of the phi squared term in the Lagrangian. So very roughly, whether this term dominates depends on the value of the scalar field, just what the magnitude of the field is. Field satisfies a Poisson equation, similar to the Newtonian potential. If the field's massless, it satisfies exactly the same Poisson equation, but with a different coefficient. If it has some mass, it's a Klein-Gordon equation that also has a mass term. But roughly what that means is that it's sourced by objects in the same way as the Newtonian potential. So the field behaves similarly to the Newtonian potential. So a threshold value of the field corresponds to a threshold value of the Newtonian potential. And similarly, the kinetic term is a derivative of the field. So if the field goes like the potential, the derivative of the field goes like the acceleration. And higher order terms, leading order there is second derivative. So second derivative of the field goes like second derivative of the potential, which is the space-time curvature. Okay, so I'm going to focus from now on this first mechanism, Chameleon. There are two reasons for that. First one is that that's the one that actually gives the astrophysical signals that I'm going to be talking about in a few minutes. Second one is that you might have heard that the recent observation of gravitational waves with an electromagnetic counterpart put quite strong constraints on a number of modified gravity theories. What that really did is put Weinstein screening in serious trouble. So the paradigmatic example of a Weinstein screened theory is a Galilean gravity, where the scalar field just has a Galilean symmetry. The two of the surviving Galilean models were completely ruled out by the gravitational wave event with electromagnetic counterpart. And the third one actually predicts the wrong sign for integrated Sachs-Wolf, so that's also kind of in trouble. But Chameleon screened models were completely unaffected by that. They naturally predict that gravitational waves travel at the same speed as light. So that parameter space is as open as it was before that. Okay, so I'm going to focus now on Chameleon. And I'll start by giving you a little more evidence for why Newtonian potential ought to be considered a good proxy for how screened an object is. So this is an n-body simulation in f of r gravity. Each of the points here are halos produced in the simulation. They're color-coded by how screened the halo is. So these black points and blue points here are strongly screened, and the red points are unscreened. And what they're plotted against are, over here we've got the external Newtonian potential that's sourced by surrounding masses around that test halo. And on the x-axis is the mass of the halo itself. So you can see that for an object to be screened, either it can be in a region that has strong external, is in a deep external potential well. So we'd call that environmentally screened. It's screened by the surrounding masses. Or alternatively, it can be high enough mass that it screens itself. That's called self-screening. And so roughly the sum of these two is the total potential that the object feels. If that total potential is greater than a certain value, then it's screened, and otherwise it's unscreened. Okay, so
these calculations, what approximations are made
to calculate which?
A lot of people drop some terms when they do vector gravity because they're working in the JB frame.
So it's Husavicki, f of r gravity. I'm not sure whether they drop any terms. I didn't know that they did, but
It's usually a dynamic term, they say it's small, but...
Did they do that even in...
So it's kind of curious, but it is...
Okay. Yeah, I don't know. That's a good question. I'll take a look at this paper. Yeah. Okay. So then here's my sort of overview of how I'm going to use all that information to try to make a test of Chameleon screened fifth forces. So the first thing is to map out these gravitational variables over the local universe. That'll tell us whether a given object is screened or unscreened. If it's in a deep enough potential well, it will be screened. And if it's in a sparse environment, it will be unscreened. Then I can use that to forward model some signals, which I'll show you in a moment, for what a screened fifth force actually does within galaxies, and then constrain the two effective parameters of the fifth force, its strength and its range, based on that. Okay, so are there any other questions so far? This is sort of the end of the introduction. Okay, so first off, how do we go about determining whether an object is screened or not? So that amounts, as I say, to determining mainly what the Newtonian potential of a given object is. Of course, in principle, that's very easy to calculate. You just take a given test object and sum up the contribution to the Newtonian potential, just an m over r term, from all surrounding masses. But of course, in practice, in the real universe, that's very difficult to do because most of the mass is dark matter and we don't know where it is. So to try and deal with that, I've got a three-step method that I developed for this paper that I wrote last year, and you can find all the details of it there. So the first contribution comes from just objects that we can see, as in galaxies in a galaxy survey, in a redshift survey, and in this case, 2m++ survey, which is all sky, with a magnitude limit in the K-band of 12.5. So many objects, of course, are fainter than that magnitude limit, which means we don't see them. So what do we do about them? Well, to get a handle on their contribution to the potential, we can have a look in simulations. So what I did here was took an n-body simulation, populated it with galaxies according to our best models of the galaxy halo connection, and then split that galaxy population into ones that we would see in 2m++ and ones that we wouldn't see. And then determined what the correction was to the potential due to the objects that we couldn't see. And then the third contribution is, of course, that not all mass is actually associated with halos in the universe at all. A lot of it is in longer wavelength modes of the density field. And so to get a handle on that, I used the reconstructions of the long wavelength modes of the density field from this Borg algorithm. I don't know if you've heard of it, developed by Guillaume Leveau and Jens Jascher, which is basically a way of reconstructing the redshift 0 density field and also the initial conditions by forward modeling galaxy number densities and peculiar velocities in 2m++, assuming a bias model and cosmology and so on. So you put all those three contributions together and you have some idea of what the potential field of the universe is. Then you can take a given point in space and you can ask what its total Newtonian potential is, and that should tell you whether or not it's screened.
Okay, so you got a halo contribution, and did you embed that into the smooth mass density contribution, or is that separate?
Yeah, so the way I've done it here, it's separate. Sorry, it's separate, the way I've done it so far, which means this actually overestimates the potential a little bit because you're including some of the same mass twice.
And the halo distribution goes up to what distance?
Oh, you mean what the masses of the halos are?
You have a halo, right?
Yeah.
Halo has extension.
Right. So I assumed an NFW profile that just...
And where did you truncate?
It'll be R200.
Say that again?
R200. 200 times row crit. Yeah.
It was R200.
Yeah, I think so.
R200C.
Yes, I believe so, but I can check that. Okay, so these plots at the bottom show the relative sorry, I'll try and speak up. Show the relative contribution to these three gravitational variables from each of these contributions. So I won't go into it in detail, but just to point out that, of course, the Newtonian potential is sensitive to larger scale features than the curvature because it goes as 1 over r rather than 1 over r cubed. So in general, that one's more dependent on the sort of smoother mass that's distributed in longer wavelength modes, which is this green line here, relative to curvature, which is more sensitive to the mass in collapsed objects. It's actually in halos. Okay, so we can see that some more here. So what these show, these are just contour plots of the potential, acceleration, and curvature across a 150 by 150 megaparsec slice of the local universe. And these show the corresponding distributions of values of these variables across the galaxies in the 2M++ survey. So you can use these maps to just try and isolate regions of the local universe whose gravitational fields have certain properties. So if you want to look in regions of low potential, which are the most likely to contain unscreened objects, then that's these blue regions here. And all the code for doing this is on my website. So if you have any applications for this kind of thing, then you can just take a look at it there or ask me about it. Okay, so now let me be a little bit more precise about using that to determine which objects are screened versus unscreened. So I'll focus here on a simple f of r model called Husavicki. That's described by a single degree of freedom, which goes by the name of FR0. That's just it's the derivative of the f function in f of r evaluated at current cosmological value of the Ricci scalar. And that parameter determines both what the range of the fifth force is, the range of the scalar field, that's this lambda c, and it also determines what the threshold value of Newtonian potential is that divides screened from unscreened objects. So for example, if I take FR0 to be 10 to the minus 6, that's a kind of roughly still viable model of f of r. It's beginning to be constrained by some astrophysical measurements. I calculate what the range of the scalar field is. The range is about 3 megaparsec. So objects further apart than 3 megaparsec don't interact with one another via the fifth force, even if they're unscreened. And it has a threshold value of potential for screening of, 1.5 times 10 to the minus 6. So I take this red histogram here. That corresponds to including the contributions out to 3 megaparsec, as in a range for the fifth force of 3 megaparsec. And then I draw this dividing line at a potential of 1.5 times 10 to the minus 6. All the objects in this part have lower potentials than the threshold, so they're unscreened. And all the objects above are screened. And you can play a similar game with other values of FR0. So essentially, once you've fixed a certain modified gravity model that you want to look at, then you can calculate what the threshold value of the Newtonian potential is, and then split galaxies into screened and unscreened populations. And the idea then is that they should be behaving differently to one another. So only the unscreened subset manifests the fifth force. So if whatever observational signals there are of a fifth force, which I'll come to in a moment, you should only see in the unscreened sample. Okay, any other questions on that? Okay, so now I'm going to talk about what those signals actually are that we should see in unscreened galaxies. So there are 4 of them, and they're all laid out in this nice paper by Booth Jane and Jake van der Plas in 2011. I'll talk about two of them here. They all come from the same basic effect, which is that if you take a galaxy that's overall unscreened, so it's in a low density region, it's not environmentally screened, it's also low mass, so it's not self-screened. That means the gas and dark matter in it feel a fifth force. They interact with each other and with surrounding mass via a fifth force. Stars, on the other hand, are also massive objects, so they screen themselves. They can screen themselves. Stars have Newtonian potentials at their surface, main sequence stars, of around 10 to the minus 6. So as long as this threshold value for screening is less than 10 to the minus 6, stars will always be screened, no matter where they are. They'll always be self-screened. So that does some interesting things, then, right? If you have a galaxy in an external fifth force field, that causes the gas and dark matter to accelerate in the direction of that field, but not the stars. So the stars lag behind the gas and the dark matter. And they lag behind to such an extent, well, until the extra force that they feel due to their offset from the center of the halo exactly compensates for their not feeling the fifth force. So it's just an equilibrium configuration. And if that's satisfied, then the total acceleration of all the parts of the galaxy will be the same. So the galaxy will stay together. And that's described by this equation here.
What sort of threshold density do you have in mind here?
So the threshold values of Newtonian potential are something like 10 to the minus 6 to 10 to the minus 8, which is a fair fraction of the environments of the local universe. Yeah, that's an interesting point. So what I mean by potential here is just like a sum of gm over r from all mass that's within the range of the scalar field.
I'm just thinking of the obvious thing of you could talk about stars, but the solar system on average is a big density fluctuation, or galactic distance fluctuation. And I thought all of these things were way above threshold.
Exactly. So stars and the Milky Way have Newtonian potentials about 10 to the minus 6 at their surface. So as long as your threshold is below that, they will always be screened. And indeed, you need the Milky Way to be screened, because the whole point of screening is that you reproduce GR with the solar system tests and so on. Does that answer your question? Okay. Maybe we can carry on later. Okay. So that equilibrium is described by this equation here. So this is just the extra force that the gas and dark matter are feeling due to their interaction with the fifth force. In equilibrium, that has to equal this restoring force that the stellar disk feels due to its offset from the center of the halo. So this is an implicit equation for the separation between the center of the halo and the center of the disk, r star. Of course, that's only true if the galaxy as a whole is unscreened. If the galaxy is screened, then all the mass components in it are screened, so nothing happens. It doesn't do anything. Okay, so this is actually not very difficult to test observationally. We know how stars emit. They emit in optical wavelengths or thereabouts, and we know how gas emits. That is mostly atomic hydrogen. It emits in H1, which we see as 21 centimeter radiation. So the basic idea behind this test is just to cross-correlate a sample of galaxies measured with H1 emission, in this case alpha, with optical measurements, for example, from SDSS. So the H1 will trace the gas, the optical emission will trace the stars, and whatever differences there are in the centroids of those emission will be some estimate for how the gas and stars have separated from one another. And the idea is to see if that correlates in some way with whether a galaxy is screened or not, and what the magnitude of the fifth force acceleration at the position of the galaxy is. So what I'm going to do is forward model that signal for all galaxies in the alfalfa dataset. So alfalfa is a blind H1 survey out to about redshift 0.06. Final data release was earlier this year. It's about 10,000 galaxies. Most of those have corresponding detections from SDSS. So for each galaxy in the sample, I have an RN deck position of H1 centroid of emission, and an RN deck for optical emission. That's the data. The model is just solving this equation to calculate for a given galaxy and for given parameters describing the fifth force what the separation should be on the plane of the sky. So I give you some more details of that here. So as I just said, the predicted value of R star depends on three things. It depends on the strength of the fifth force, the range of the fifth force, which also sets the threshold value of Newtonian potential. It depends on the gravitational environment, which determines whether or not the galaxy is screened, and it also determines how strong the fifth force is at the position of the galaxy. And it depends on the internal properties of the halo, and in particular what this mass enclosed within the offset is. So if I have estimates of all those things for each of the galaxies in the survey, then I can make a prediction for what that offset R star should be. And so the way I'll do that, so one of the features of this that I put some effort into developing was not only to calculate a kind of maximum likelihood estimate for each of these things, but also to model their uncertainties at the same time. So each of these inputs, rather than being a single value for a given galaxy, is actually a probability distribution. And then I'll use Monte Carlo sampling to propagate the uncertainties in those distributions into an uncertainty in the predicted value of this offset R star for a given galaxy. And that's encapsulated in this likelihood model here. Right, so what is this? What's going on? This is the likelihood for galaxy I to have observed separation R star, which, as I say, is something you can just measure from this cross-correlation of alfalfa and SDSS, as a function of these parameters, which are the ones we care about. Has two terms. First term is just what happens if the galaxy is screened. If the galaxy is screened, then the fifth force model predicts that R star has to be 0. There's no separation between stars and gas if the galaxy is screened because no fifth force is doing anything. There's some probability for the galaxy to be screened given by 1 minus f. That just comes from propagating the uncertainties in these various inputs to the model. Then second term is contribution to the likelihood if the galaxy is unscreened. So what I have there is, as I say, I have Monte Carlo realizations of the inputs to the model. So if I have n realizations, then I have n possible values for R star for each galaxy, and I'll use that to build an empirical likelihood function. That sort of histogram of those 1,000 values is essentially the likelihood function of R star given this model. So this is just a discretized version of that with some probability f for the galaxy to be actually unscreened. Okay. So that's one component of the likelihood. There's of course another one, which is due to noise in some way. So this model, as it stands, predicts that there's no way to get a separation between stars and gas unless there's a fifth force. That's of course not true. There are at least two ways to get a separation even if there's no fifth force. One is just measurement uncertainty. The true value of the offset could be 0, but because we have some uncertainty in the spatial positioning of H1 emission as it's measured on the sky, we would still observe some difference. And the second one is that there are, of course, astrophysical effects that can lead to differences in the spatial positions of stars and gas in standard gravity. So, for example, ram pressure affects gas, but not stars. Hydrodynamical drags. Feedback can influence these two components differently. So the way I'll deal with that is just convolve the likelihood that I wrote down with some kind of Gaussian that describes the overall amount of noise that you have in a given galaxy. So the width of that Gaussian is this sigma I here. This is just the same equation that I wrote down before, but convolved with this Gaussian, so smearing out the delta functions into distributions with some width. And then the overall likelihood of the entire data set will just be product of all these likelihoods, assuming that the galaxies are behaving independently. And assuming also that the two components of this signal on the plane of the sky are independent, right? So the signal is two-dimensional. So there's effectively two independent components, which I resolve in the RA and DEC directions for a given galaxy, but it doesn't matter as long as they're orthogonal to one another. Okay, so let's see. Okay, so I'll say a bit more about the noise in a bit, but let me move on to showing some results on this. So look at the top left plot. What this is showing, so each point here is a galaxy in the data set. I've plotted on the y-axis the expected value of this offset for some fiducial fifth force model, one where the modification to gravity is quite strong and with a range of 5 megaparsec. And on the x-axis is the value of Newtonian potential at that galaxy, which determines whether or not it's screened. So look at the red points. They're for the full model with screening. So galaxies that lie above this dotted line, this dashed line, that's the threshold value of potential for this model. If a galaxy has higher potential, it's screened, so this signal drops to nothing. And if it has lower potential, then you see some offset. And in this case, the offsets between the stars and gas are of order 1 kiloparsec, which is quite large, but as I say, this is for a very strong modification to gravity. This error bar here is just the width enclosing 68% of the Monte Carlo realizations of the model. So just some idea of what the 1 sigma uncertainty.
Can you say a little more about lambda 5 megaparsecs? So much earlier you were dealing with the Yukawa.
Yeah.
But this is not a lambda Yukawa.
Yeah, that's right. So I've actually.
What exactly is it?
It's a top hat. I've cut off the fifth force after the range. So I'm saying that within this 5 megaparsec, it has a 1 over r squared contribution, so it behaves like normal gravity. If objects are within 5 megaparsec, it's physical. This is all at redshift 0, essentially.
So within our galaxy,
Yeah.
are you saying that up to 5 megaparsecs there's no effect?
Well, our galaxy is screened anyway, so our galaxy is not sourcing any fifth force.
Which is the whole interior is screened.
The whole interior of the Milky Way, for sure, is screened.
Yeah.
What we're seeing signals here for, all these galaxies in red here, are lower density, lower mass objects than the Milky Way.
The way you transitioned was a sharp transition as opposed to a positive transition.
That's right. So all I've done is approximated
This
this.
is the kind of approximation that we use, but the people that make the approximations in the end body, they don't do that at all. I mean, they actually, for them, the Laplacian scale is the most fundamental thing, which I think is an incorrect description of the development of the medium.
Yeah. Yeah, it's an approximation. I mean, it can break down, of course, and we can talk about that.
I'm not exactly sure exactly how you implement the 5 megaparsecs, but I've got a better idea of what it's all about.
Okay, good. So the plot down here is the same thing, but plotted against the fifth force acceleration. So there's a strong positive correlation here, obviously, because the value of R star is just proportional to how strong the fifth force field is at the position of a galaxy. And this correlation with potential just derives from that. So phi and A are correlated because they're sourced by the same mass distribution. So this is just a slightly blurred out version of this.
Is there a reason why there's two lines in that plot? Like there seems to be a big blob at the top and a small.
Yeah, it's a good question. I don't know, actually. I don't know why that is. I don't know whether there are somehow like two slight. Yeah, I don't know. I thought about that too, but I haven't. Nothing's jumped out at me as being a major difference between the galaxies that lie in those two blobs. So I don't know. I mean, it's a bit hard to see because it's sort of saturated with points in here, so it might not really be significant at all. Okay, and then on the right, I've just shown exactly the same thing, but replacing the predicted value of the offset by the observed value. So you can see a number of things. Firstly, there's not any evident correlation with the Newtonian potential or with the acceleration. Secondly, so the offsets are of order 10 kiloparsec, or well, 1 to 10 kiloparsec. That's mainly because the resolution in the H1 measurements are pretty poor. So it's something like 20 arc-second uncertainty in the spatial positioning from alfalfa. Propagate that out to 100 megaparsec, and you've got some pretty big uncertainties. Okay, so what this tells us is that if there's any contribution of this signal that's coming from a fifth force, it has to be quite a small fraction of the total. It has to be mostly noise-dominated, this system, because otherwise you would see some of these features, like you would see something happening beyond the threshold value beyond some threshold value of Newtonian potential, or you'd see this correlation. Yeah, okay. Well, how much time do I have?
You have about 10 more minutes left.
Okay, good. So I'll skip over a little bit. Okay, so here is a money plot, not the money plot, but a money plot. So I need to talk a little bit more about the noise before I say this. So remember the way I treated the noise was I convolved the fifth force likelihood with a Gaussian that just smeared it out. And there's a parameter, sigma, in that Gaussian that determines how much it's smeared out. So I just told you that the signal was largely noise dominated. Most of this dispersion that we see is just either measurement uncertainty or it's something unrelated to a fifth force. That means fifth force contribution has to be a small perturbation on top of that. So on the whole, that Gaussian component to the likelihood describes to first order, that Gaussian component describes the data. Fifth force is a little bit on top of that. So the way I can set this sigma that I have here in the Gaussian is just to set that equal to the standard deviation of the data in bins, in this case, of signal to noise of the detection. So again, what that's saying is just that to leading order, the component of the likelihood that comes from noise, which is just a Gaussian, has nothing to do with the fifth force, fully accounts for the dispersion in the data to first order. And then there's a little perturbation on top of that, potentially, that can describe a contribution, a small fractional contribution of the fifth force. Okay, so for reasons that I'll show you in a moment, I'm going to start by taking a very conservative value for what that noise is. That noise is going to be not the standard deviation of the measurements, but twice the standard deviation of the measurements. So that's just saying that it's very noise dominated. The uncertainties are very large. And if you do that, you can set these constraints on what the strength of the fifth force has to be as a function of range, just using standard Bayesian inference based on that likelihood and comparing to that alfalfa plus SDSS data. So here they are. They're quite nice. We're probing values of the strength of the fifth force, about 1%, that of gravity, for ranges of order 1 megaparsec or 10 megaparsec. I've got these two models here. They're not particularly important. The red one is the full model with screening. The green one is something very similar, except with screening turned off. So in that case, all galaxies count as being unscreened. So all galaxies interact via the fifth force, which gives you stronger constraints, just because all the galaxies are then contributing to the constraint rather than only the unscreened ones, which is the case for the red here. Okay, so that's fine, but it's kind of dodgy to to double the noise like this. One way to think about that is just in a model comparison sense. So what I've done there is I've said that the width of this Gaussian that describes the noise is actually twice as large as it needs to be to describe the data. So that gives you a much lower likelihood for the data than if you used a Gaussian with the same width as the data. Another way of justifying that is shown here. So what I've done here is instead of just asserting that sigma a priori, the width of the noise distribution, I've taken it as a free parameter and constrained it along with the fifth force parameters. So for example, in this plot, I just take that sigma, which, well, this is what it is in arc seconds. So as I said, about 20 arc seconds is the spatial resolution of alpha alpha. I've just taken that as a universal free parameter over the entire sample and constrained it along with the strength of the fifth force. What that gives you out is that the width of that component should indeed be the same as the width of the offset in the data. And you can do other various models like correlate that with signal to noise and so on, and effectively you get the same thing all the time. Okay, so that's intended to justify what I'm calling the fiducial noise model, which is that the Gaussian describing the noise is the same width as the data. So now let's do the same kind of thing. Let's just repeat the inference with that. Well, if you do that, then you get this. So I'm not showing you constraints here. I'm showing you an increase in the overall log likelihood of the model that you can get for any value of delta G, any value of the strength of the fifth force, as a function of its range. So you can see there's some kind of peak here, right? You get a big increase in the log likelihood of the model by putting in some component to the likelihood that ostensibly describes a screened fifth force of 2 megaparsec range. If you put in a model without screening, then you don't really get any coherent increase in the log likelihood. You just get some bumps that seem to describe noise in the inference. Okay, so I don't really have much time, but I'm going to say a few things that seem to be saying that there's some evidence for there being a screened fifth force in here. I want you to interpret that not as successful validation of a fifth force interpretation, but as a failed falsification of a fifth force interpretation. Okay, so first you can see there's this coherent trend in the likelihood as a function of lambda c. You sort of expect that because the fifth force field for different ranges, for nearby ranges, are correlated with one another. So if I have a true model with a range of around 2 megaparsec, and then I reconstruct it with a model of a range 3 megaparsec, I also expect to see some increase in log likelihood from that model, simply because the values of the potential and the acceleration are sort of similar between those two. Also, as I say, the model without screening doesn't give you any significant increase in log likelihood. That's sort of surprising if you thought that this was coming from some kind of hydrodynamical effect, like some of the systematics that I mentioned, because it's saying that it's sensitive, this increase in log likelihood is sensitive to which objects are screened and which are unscreened. And that's some complicated function of their gravitational environment described by Newtonian potential. So that seems a little bit hard to mock up by other means. So I'll skip a couple of things here. So some more things you can do to try and investigate this further. One thing is repeat the analysis on mock data where there's just noise, mock data that's generated entirely by noise. If you do that, then you don't see any increase in log likelihood by fitting a model with screening. Something else you can do is inject data that has the best fit values of those fifth force parameters, and then reconstruct them using a similar model. And that just tests for biases in the reconstructed value of the strength of the fifth force. So if you put in a value of 0.025, which was that maximum likelihood point that I just showed, then you also get out this is doing it for lots of times, marginalizing over realizations of the noise, you also get out something very similar. You can repeat for bootstrap and jackknife resamples of the data. So asking whether there's some peculiarity of the specific alfalfa sample that's relevant for that result, or whether it would also be expected to be seen in similar types of data. You find, okay, so bootstrap, as you know, you take draws from the sample but with repeats, so you have the same galaxy multiple times. That reduces your statistics, so you're less likely to find a significant discrepancy from the case where there's only noise. And similarly, jackknife, you just have a smaller sample size, so the same thing is true. But on the whole, you still see that there's some, that most of these samples have a significant discrepancy with the case where there's nothing, where there's only noise. And they also reconstruct the right values of delta G. And finally, before I stop, so if there's any component of this signal that's coming from a fifth force, the way that's determined is that on average, the direction of the offset on the plane of the sky should be positively correlated with the predicted direction from the fifth force, which is the direction of the fifth force field at that point. So clearly what that means is that if you arbitrarily rotate the direction of the fifth force field, then that should make the signal go away. Okay, this is turning it through 180 degrees. If I turn it through 180 degrees, then your posterior peaks at 0, as you expect. Then instead of correlating the fifth force with the observations, you're anti-correlating it. So you expect to get a strong constraint. Similarly, if you rotate it through 90 degrees, then the signal at least weakens, if not going away completely. Okay, and I've got no time, do I? Okay, well, I'll just end there, actually, then. Yeah, that's fine. I have a second half to this, sort of, but that'll have to wait for another date. And actually, it's good that it should wait, because the paper's not out yet. So I'll save that for my next CITA seminar.
So, in terms of improving this analysis from the data side, what's your ideal data set? Or do you just want more statistics? Do you want super alfalfa with better resolution?
Yeah, super alfalfa with better resolution is what I want, otherwise known as SKA, actually. Okay, there are two issues here. I mean, one is just statistical uncertainty. So the resolution of the H1 mapping is not very good, which is why there's a big dispersion in the data that you see. Alfalfa about 20 arcsec resolution, SKA less than 1 arcsecond, and much bigger sample sizes. So, right, that'll just do this analysis a whole lot better. But the other thing, of course, is systematic errors. Actually, sorry, I'll flash this up while I'm talking. So there are a bunch of systematic errors in this, and one of which I mentioned, which is that there are other types of physics, what we call galaxy formation physics or baryonic physics, which can also mess around with your stars and gas differently. And we don't really have much of a model for what that kind of physics should do here. But that's not a data question, that's more of a modeling one. So one of the things that I think you can look at there is go into hydro sims, for example, and see what kind of signal you see in those. And maybe use that to improve the component of the likelihood function that's not coming from a fifth force in this inference that I have.
Yep. All right, let's thank Harry again.